हेलो फ्रेंड्स, तो राना अकेडमी में आपका स्वागत है। हम स्टार्ट करने जा रहे हैं 11th क्लास की केमिस्ट्री, जिसमें हम स्टार्ट करेंगे यूनिट 4 केमिकल बॉन्डिंग एंड मॉलिक्यूलर स्ट्रक्चर, नीट फॉर एनसीईआरटी। Scientists are constantly discovering new compounds, orderly arranging the facts about them, trying to explain with the existing knowledge, organizing to modify the earlier views or evolve theories for explaining the newly observed facts. Matter is made up of one or different type of elements. Under normal conditions, no other element exists as an independent atom in nature, except noble gases. However, a group of atoms is found to exist together as one species having characteristic properties. Such a group of atoms is called a molecule. Obviously, there must be some force which holds these constituent atoms together in the molecules. The attractive force which holds various constituents, atoms, ions, etc., together in different chemical species is called a chemical bond. Since of the formation of chemical compounds take place as a result of combination of atoms of various elements in different ways, it raises many questions. Why do atoms combine? Why are only certain combinations possible? Why do molecules possess definite shapes? To answer such questions, different theories and concepts have been put forward from time to time. These are causal one with causal one with causal Lewis approach, valence shell electron pair per repulsion, VS EPR theory, valence bond VB theory and molecular orbital MO theory, and the evolution of various theories of valence and the interpretation of the nature of chemical bonds have closely been related to the developments in the understanding of the structure of atom, the electronic configuration of elements, and the predictable. Every system tends to be more stable and bonding in nature's way of lowering the energy of the system to attain stability. Causes Lewis' approach to chemical bonding. In order to explain the formation of chemical bond in terms of electrons, a number of attempts were made, but it was only in 1916 when Caucel and Lewis succeeded independently in giving a satisfactory explanation. They were the first to provide some logical explanation of valence, which was based on the inertness of noble gases. Lewis pictured the atom in terms of a positively charged kernel, the nucleus plus the inner electrons, and the outer shell that could accommodate a maximum of 8 electrons. He further assumed that these 8 electrons occupy the corners of a cube which surrounded the kernel. Thus, the single outer shell electron of sodium would occupy one corner of the cube, while in the case of noble gas, all the 8 corners would be particularly stable electronic configuration. Lewis postulates that atoms achieve the stable octet when they are linked by chemical bonds. In the case of sodium and chlorine, which can happen by the transfer of the electron from sodium to chlorine, thereby giving the sodium ion and potassium ions. In the case of other molecules like chlorine, hydrogen, boron, etc., the bond is formed by the sharing of a pair of electrons between the atoms. In the process, each of atom contain a stable outer octet of electrons. Lewis symbols in the formation of molecule. Only the outer shell electrons take part in a chemical combination, and they are known as valence electrons. The inner shell electrons are well protected and are generally not involved in the combination process. Jean Lewis, an American chemist, introduced the simple notations to represent valence electrons in an atom. These annotations are called Lewis symbols. For example, the Lewis symbols for the elements of second period are as under. lithium, beryllium, boron, carbon, nitrogen, oxygen, boron, neon. Significance of Lewis symbols. The number of dots around the symbol represents the number of valence electrons. This number of valence electrons helps to calculate the common group valence of the element. The group valence of the elements is generally either equal to the number of dots in Lewis symbols of or 8 minus 8 minus the number of dots or valence electrons. The Cosell in relation to chemical bonding drew to the following facts. Now, in the periodic table, the highly electronegative halogens and the highly electropositive alkali metals are separate by the noble gases. The formation of a negative ion from a halogen atom and a positive ion from an alkali metal atom is associated with the gain and loss of an electron by the respective atoms. The negative and positive ions thus formed at unstable noble gas electronic configurations. And the noble gases, with the exception of helium, which has a duplet of electrons, have a particularly stable outer shell configuration of 8 octet electrons Ns2 Np6. The negative and positive ions are stabilized by electrostatic attraction. For example, the formation of NaCl, sodium chloride, and sodium and chlorine, according to the above scheme, they can be explained as sodium, potassium, sodium N plus Na plus ion plus E electron, neon 3s1 neon, chlorine plus electron then gives chlorine ion, neon 3s2 3p2, neon 3s2 3p6, or argon. And so sodium ion and chlorine ion then gives sodium chloride or NS positive Cl negative. Similarly, the formation of CaF2 may be shown as the bond formed as a result of the electrostatic attraction between the positive and negative ions was termed as the electronic bond. The electrovalence is thus equal to the number of unit charges on the ion. Thus, calcium is assigned a positive electrovalence of 2, while chlorine has a negative electrovalence of 1. The Cosell's postulations provide the basis for the modern concepts regarding ion formation by electron transfer and the formation of ionic crystalline compounds. His views have proved to be of great value in the understanding and systematization of the ionic compounds. At the same time, he did recognize the fact that a large number of compounds did not fit into these concepts. Octet rule. Cosell and Lewis in 1916 developed an important theory of chemical combination between atoms known as electronic theory of chemical bonding. According to this, atoms can be combined either by transfer of valence electrons from one atom to another, gaining or losing, or by sharing of valence electrons in order to have an octet in their valence shell. This is known as octet rule. Covalent bond. Langmuir 1919 refined the Lewis postulation by abandoning the idea of the stationary cubical arrangement of the octet and by introducing the term covalent bond. The Langmuir the theory can be understood by considering the formation of the chlorine molecule Cl2. The chlorine atom with the electronic configuration neon 3s2 3p5 is one electron short of the argon configuration. The formation of Cl2 molecule can be understood in terms of the sharing of pair of electrons between the two chlorine atoms. Now each chlorine atom contributing one electron to the shared pair. In the process, both chlorine atoms attain the outer shell octet of the nearest noble gas, argon. The dots represent electrons. Such structures are referred to as Lewis dot structure. Lewis dot structures can be written for other molecules also, in which the combining atoms may be identical or different. The important conditions being that each bond is formed as a result of sharing of an electron pair between the atoms. Each combining atom contributes at least one electron to the shared pair. The combining atoms attain the outer shell noble gas configurations as a result of sharing of electrons. Thus, in water and carbon tetrachloride molecules, formation of covalent bonds can be represented as. Thus, when two atoms share one electron pair, they are said to be joined by a single covalent bond. In many compounds, we have multiple bonds between atoms. The formation of multiple bonds envisages sharing of more than one electron pair between two atoms. If two atoms share two pairs of electrons, the covalent bond between them is called a double bond. For example, in the carbon dioxide molecule, we have two double bonds between the carbon and oxygen atoms. Similarly, in the ethane molecule, the two carbon atoms are joined by a double bond of CO2 molecule. When combining atoms share three electrons pairs, as in the case of two nitrogen atoms in a N2 molecule, and the two carbon atoms in the ethyl molecule, the triple bond is formed. Lewis representation of simple molecules, or the Lewis structure. The Lewis dot structure provide a picture of bonding in molecules and ions in the terms of the shared pairs of electrons and the octet rule. While such a picture may not explain the bonding and behavior of molecule completely, it does help in understanding the formation and properties of molecule to a large extent. Writing of Lewis dot structure of molecule is therefore very useful. The Lewis dot structures can be written by adopting the following steps. The total number of electrons required for writing the structures are obtained by adding the valence electrons of the combining atoms. For example, in a CH4 molecule, there are 8 valence electrons available for bonding, 4 from carbon and 4 from the 4 hydrogen atoms. For 4 anions, each negative charge would mean addition of 1 electron. For cations, each positive charge would result in subtraction of 1 electron from the total number of valence electrons. Now, for example, for the CO3 dinegative ion, the two negative charges indicate that there are two additional electrons than those provided by the neutral atoms. For the NH4 positive ion, the one positive charge indicates the loss of one electron from the group of neutral atoms. Knowing the chemical symbols of the combining atoms and having knowledge of the skeletal structure of the compound known or guessed intelligently, it is easy to distribute the total number of electrons as bonding shared pair between the atoms in proportion to the total bonds. In general, the least electronegative atom occupies the central position in the molecule ion. For example, in the NF3 and CO3, dinegative nitrogen and carbon are the central atoms, whereas fluorine and oxygen occupy the terminal positions after accounting for the shared pairs of electrons. For single bonds, the remaining electron pairs are either utilized for multiple bonding or remain as the lone pairs. The basic requirement being that each bonded atom gets an octet of electrons. Lewis representations of a few molecules ions are given in table 4.1. The Lewis representation of some molecules. Problem 4.1, write the Lewis dot structure of CO molecule. Count the total number of valence electrons. Step 1. Count the total number of valence electrons of carbon and oxygen atoms. The outer valence shell configurations of carbon and oxygen atoms are 2s2, 2p2 and 2s2, 2p4 representatively. Now the valence electrons available are 4 plus 6, 10. To step, the skeletal structure of CO is written as CO. Third step, draw the single bond one shared electron pair between carbon and oxygen and complete the octet on O. The remaining two electrons are the lone pair of carbon, and this does not complete the octet on carbon, and hence we have to resort to multiple bonding. In this case, a triple bond between carbon and oxygen atoms. This satisfies the octet rule condition for both atoms. Problem 4.2. Write the Lewis structure of nitrite ion NO2 negative. Solution for step 1. Count the total number of valence electrons of the nitrogen atom, the oxygen atoms, and the additional one negative charge equal to 1 electron. Nitrogen 2s2 2p3, oxygen 2s2 2p4, 5 plus 2 into 6 plus 1 is equal to 18 electrons. The skeletal structure of NO2 negative is written as the O and O. Draw a single bond, one shared electron pair between the nitrogen and each of the oxygen atoms, completing the octets on oxygen atoms. This, however, does not complete the octet on nitrogen if the remaining two electrons constitute lone pairs on each oxygen, nitrogen, oxygen. Hence, we have to resort to multiple bonding between nitrogen and one row of the oxygen atoms. In this case, the double bond. This leads to the following Lewis dot structure: formal charge. Lewis dot structures in general do not represent the actual shapes of the molecules. In case of polyatomic ions, the net charge is possessed by the ion as a whole and not by a particular atom. It is, however, feasible to assign a formal charge on each atom. The formal charge of an atom in a polyatomic molecule or ion may be defined as the difference between the number of valence electrons of that atoms in an isolated or free state of and the number of electrons assigned to that atom. In the Lewis structure, it is expressed as a formal charge on the atom. In the Lewis structure, total number of valence electrons in the free atom, total number of non-bonding minus total number of non-bonding lone pair electrons minus half total number of bonding shared electrons. The counting is based on the assumption that the atom in the molecule owns one electron of each shared pair and both the electrons of a lone pair. Let us consider the ozone molecule O3. The Lewis structure of O3 may be drawn as the atoms have been numbered as 1, 2, and 3. The formal charge on the central O atom marked 1 6 minus 2 minus half into 6 is equal to plus 1. The end O atom marked 2 6 minus 4 minus half into 4 is equal to 0. The end O atom marked 3 6 minus 6 minus half into 2 is equal to minus 1. Hence, we represent O3 along with the formal charges as follows. We must understand that formal charges do not indicate real charge separation within the molecule. Indicating the charges on the atoms in the Lewis structure only helps in keeping track of the valence electrons in the molecule. Formal charges help in the selection of the lowest energy structure from the number of possible Lewis structure for a given species. Generally, the lowest energy structure is the one with the smallest formal charges on the atoms. The formal charge is a factor based on a pure covalent view of bonding in which electron pairs are shared quality by neighboring atoms. Limitations of the octet rule. The octet rule, through useful, is not universal. It is quite useful for understanding the structures of most of the organic compounds, and it applies mainly to the second period elements of the periodic table. Now, there are three types of exceptions to the octet rule. The incomplete octet of the central atom. In some compounds, the number of electrons surrounding the central atom is less than 8. This is especially the case with the elements having less than 4 valence electrons. Examples of lithium chloride, barium hydrogen, and boron chloride. Lithium chloride, HbH, BCl3, BCl3. Lithium, beryllium, boron have 1, 2, and 3 valence electrons only. Some other such compounds are aluminum chloride, AlCl3, and boron fluoride, BF3, at odd electron molecules. In molecules with an odd number of electrons, like nitric oxide NO and nitrogen dioxide NO2, the octet rule is not satisfied for all the atoms NO. The expanded octet elements in and beyond the third period of the periodic table have, apart from 3s and 3p orbitals, 3d orbitals also available for bonding in a number of compounds of these elements. Now, there are more than 8 valence electrons around the central atom. This is termed as the expanded octet. Obviously, the octet rule does not apply in such cases. Some of the examples of such compounds are from BF3, PF5, SF6, H2SO4, and a number of coordination compounds. Interestingly, sulfur also forms many compounds in which the octet rule is obeyed. In sulfur chloride, the S atom has an octet of electrons around it, SCl2. Other drawbacks of the octet theory. It is clear that octet rule is based upon the chemical inertness of noble gases. However, some noble gases, for example, xenon and krypton, also combine with the oxygen and fluorine to finish a number of compounds like ZeF2, XeF2, KRF2, XeOF2, etc. This theory does not account for the shape of molecule. It does not explain the relative stability of the molecules, being totally silent about the energy of molecule. The ionic or electrovalent bond from the Quasil and Lewis treatment of the formation of an ionic bond, it follows that the formation of ionic compounds would primarily depend upon the case of formation of positive and negative ions from the respective neutral atoms. The arrangement of the positive and negative ions in the solid, that is, the lattice of the crystalline compound. The formation of a positive ion involves ionization, that is, removal of electrons from the neutral atom, and that of the negative ions involves the addition of electrons to the neutral atom. G is equal to m plus gram plus electron ionization enthalpy, electron gain enthalpy. Electron gain enthalpy, the delta EGH is the enthalpy change. Unit 3, when a gas phase atom in its ground state gains an electron, the electron gain process may be exothermic or endothermic. The ionization, on the other hand, is always endothermic. Electron affinity is the negative of the energy change accompanying high electron gain. Obviously, ionic bonds will be formed more easily between elements with comparatively low ionization enthalpies and elements with comparatively high negative value of electron gain enthalpy. Most ionic compounds have cations derived from metallic elements and anions from non-metallic elements. The ammonium ion NH4 positive, made up of two non-metallic and elements, is an exception. It forms the cation of a number of ionic compounds. Ionic compounds in the crystalline state consists consists of orderly three-dimensional arrangements of cations and anions held together by Coulombic attraction interaction energies. These compounds crystalline in different the ions, their packing arrangements, and other factors. The crystal structure of sodium chloride NaCl rock salt, for example, is shown below. A rock salt structure in ionic solids, the sum of the electron gain enthalpy and the ionization enthalpy may be positive, but still the crystal structure gets stabilized due to the energy released in the formation of the crystal lattice. For example, the ionization enthalpy for sodium and formation of sodium is 495.8 kilojoule per mole, while the electron gain enthalpy for the change chlorine plus electron then UCl negative is a minus 348.7 kilojoule per mole only. The sum of the two, 147.1 kilojoule per mole, is more than compensated for by the enthalpy of lattice formation of NaCl minus 788 kilojoule per mole. Therefore, the energy released in the process is more than the energy absorbed. Thus, a qualitative measure of the stability of an ionic compound is provided by its enthalpy of lattice formation, and not simply by achieving octet of electrons around the ionic spaces in gaseous state. Since lattice enthalpy plays a key role in the formation of ionic compounds, it is important that we learn more about it. Lattice enthalpy. The lattice enthalpy of an ionic solid is defined as the enthalpy energy required to completely separate 1 mole of a solid ionic compound into gaseous constituent ions. Now, for example, the lattice enthalpy of NaCl sodium chloride is 788 kilojoule per mole. This means that 788 kilojoule of energy is required to separate 1 mole of solid sodium chloride ion to the 1 mole of sodium ion and 1 mole of chlorine ion to an infinite distance. This process involves both the attractive forces between ions and of opposite charges, and the repulsive forces between ions of like charges. The solid crystal being three-dimensional, now it is not possible to calculate lattice enthalpy directly from the interaction of forces of attraction and repulsion only. Factors associated with the crystal geometry have to be included. Bond parameters. Bond length is defined as the equilibrium distance between the nuclei of two bonded atoms in a molecule. Bond lengths are measured by spectroscopic X-ray diffraction and electron diffraction, the techniques about which you will learn in higher classes. Each atoms of the bonded pair contributes to the length of bond length. Figure 4.1. In the case of covalent bond, the contribution from each atom is called the covalent radius of that atom. The covalent radius is measured the covalent radius is measured approximately as the radius of an atom core which is in contact with the core of an adjacent atom. In a bonded situation, the covalent radius is half of the distance between the two similar atoms joined by a covalent bond in the same molecule. The van der Waals radius represents the overall size of the atom, which includes its valence shell in the non-bonded situation. Further, the van der Waals radius is half of the distance between two similar atoms in separate molecules in the solid. Covalent and van der Waals radii of chlorine are depicted in figure 4.2. Some typical average bond and lengths for single, double, and triple bonds are shown in a table 4.2. Bond lengths for some common molecules are given in table 4.3. The covalent radii of some common elements are listed in table 4.4. Bond angle. It is defined as the angle between the orbitals containing bond bonding electron pairs around the central atom in a molecule complex ion. Bond angle is expressed in degree, which can be experimentally determined by spectroscopic methods. It gives some idea regarding the distribution of orbitals around the central atom in a molecule complex ion, and hence it helps us in determining its shape. For example, OH bond angle in water can be represented as under 104.5 degree. Bond enthalpy. Now it is defined as the amount of energy required to break one mole of bonds of a particular type of two atoms in a gaseous state. The unit of bond enthalpy is kilojoule per mole. For example, of hydrogen bond enthalpy in hydrogen molecule is 435.8 kilojoule per mole. H2 is equal to H positive H plus H. Now delta H is equal to 435.8 kilojoule per mole. Similarly, the bond enthalpy for molecules containing multiple bonds, for example O2 and N2, will be as under O2 OO N2 NN. O2 delta H is equal to 498 kilojoule per mole. N2 N plus N delta H is equal to 946 kilojoule per mole. It is important that larger the bond association enthalpy, stronger will be the bond in the molecule. For heteronuclear diatomic molecules like HCl, we have HCl H plus Cl delta H is equal to 431 kilojoule per mole. In case of polyatomic molecules, the measurement of bond strength is more complicated. For example, in case of H2O molecule, the enthalpy needed to break the two OH bonds is not the same. H2O, HO, H plus OS, delta H1 is equal to 502 kilojoule per mole. OS plus then gives OH plus O. And then delta H2 is equal to 427 kilojoule per mole, and the difference in the delta H value shows that the second OH bond undergoes some changes because the changed chemical environment. This is the reason for some difference in energy of the same OH bond in different molecules, like C2H5OH, ethanol, and water. Therefore, in polyatomic molecules, the term mean or average bond enthalpy is used. It is obtained by dividing total bond association enthalpy by the number of bonds broken, as explained below. In case of water molecule, average bond enthalpy 502 plus 427 upon 2 is equal to 464.5 kilojoule per mole. Bond order in the Levi's description of covalent bond. The bond order is given by the number of bonds between the two atoms in a molecule. The bond order, for example, in H2 with a single shared electron pair, in O2 with two shared electron pairs, and in N2 with the three shared electron pairs, is 1, 2, 3 respectively. Similarly, in CO, three shared electron pairs between C and O. Now the two order is 3. Now for N2 bond order is 3, and its delta AH is 946 kilojoule per mole, being one of the highest of our diatomic molecule. Isoelectronic molecules and ions have identical bond orders. For example, F2 and O2 negative have bond order 1, and 2 CO and NO positive have bond order 3. A general correlation useful for understanding the stabilities of molecules is that with the increase in bond order, bond enthalpy increases, the bond length decreases. Resonance structure. It is often observed that a single Lewis structure is inadequate for the representation of a molecule in conformity with its experimentally determined parameters. For example, the ozone O3 molecule can be equally represented by the structure 1 and 2 shown below. In both structures we have OO single bond and OO double bond. The normal OO and normal OO bond lengths are 148 pm and 121 picometer respectively. Experimentally determined oxygen bond lengths in the O3 molecule are same 128 picometer. Thus and the oxygen bonds in the O3 molecule are intermediate between the double and the single bond. Obviously, this cannot be represented by either of two Lewis structures shown above. The concept of resonance was introduced to deal with the type of difficulty experienced in the depiction of accurate structures of molecules like O3. According to the concept of resonance, whenever a single Lewis structure cannot describe a molecule accurately, a number of structures with similar energy positions of nuclei, bonding and non-bonding pairs of electrons are taken as the no, as the canonical structures as of the hybrid which describes the molecules accurately. Thus for O3 the two structures shown above constituent the canonical structures or resonance structures and their hybrids, that is the three structure represents the structure of O3 more accurately. This is also called resonance hybrid. Resonance is represented by a double headed arrow. Now, some of the other examples of resonance structure are provided by the carbonate ion and the carbon dioxide molecule. Now, 4.3 problem. Now, explain the structure of CO3 trinegative ion atoms of resonance. The single Lewis structure based on the presence of two single bonds and one double bonds are between the carbon and oxygen atoms is inadequate to represent the molecule accurately as it represents unequal bonds. According to the experimental findings, all carbon to oxygen bonds and CO3 dinegative are equivalent. Therefore, the carbonate ion is based described as the resonance hybrid of the canonical forms 1, 2, and 3 shown below. 4.4 problem to explain the structure of CO2 molecule solution. The experimentally determined the carbon and oxygen bond length in CO2 is 115 picometer. Now the lengths of the normal carbon to oxygen double bonds, carbon to oxygen, the carbon and oxygen triple bond are 121 picometer and 110 picometer respectively. The carbon oxygen bond length in CO2 115 picometer lie between the values of carbon and oxygen. Obviously, a single Lewis structure cannot depict this position and it becomes necessary to write more than one Lewis structure and to consider that the structure of CO2 is best described as a hybrid of the canonical or resonance forms 1, 2, and 3. In general, it may be stated that resonance stabilizes the molecule as the energy of the resonance hybrid is less than the energy of the any single canonical structure and resonance averages the bond characteristics as a whole. Thus, the energy of the O2 O3 resonance hybrid is lower than the either of the two canonical forms 1 and 2. Figure 4.3. Many misconceptions are associated with resonance and the same need to be displayed. You should remember that the canonical forms have no real existence and the molecule does not exist for a certain fraction of time in one canonical form and for other fractions of time in other canonical forms. There is no such equilibrium between the canonical forms as we have between tautomeric forms keto and enol in tautomerism. The molecule as such has a single structure which is the resonance hybrid of the canonical forms and which are not as such are being depicted by a single Lewis structure. Polarity of bonds. The existence of a hybrid 100% ionic and covalent bonds represents an ideal situation. In reality, no bond or a compound is either completely covalent or ionic. Even in case of covalent bond between two hydrogen atoms, there is some ionic character when a covalent bond is formed between two similar atoms. For example, in H2O2, Cl2N2 and F2, a shared pair of electrons is equally attracted by the two atoms. As a result, electron pair is situated exactly between the two identical nuclei. The bond so formed is called a non-polar covalent bond. Contractory to this, in case of heteronuclear molecule like HF, the shared electron pair between the two atoms gets displaced more towards fluorine atoms gets displaced more towards fluorine, since the electronegativity of fluorine unit 3 is far greater than that of the hydrogen. The resultant covalent bond is polar covalent bond. As a result of depolarization, the molecule possesses the dipole moment depicted which below now can be defined as the product of the magnitude of a charge and a distance between the centers of positive and negative charge. It is usually designated by a Greek letter mu. Mathematically, it is expressed as follows: dipole moment is equal to charge q into distance of separation smaller. Dipole moment is usually expressed in dBs units d. The conversion factor is 1d is equal to 3.3335 of 64 into 10 to the power minus 13 cm. Now, where C is the coulomb and me is the meter. Further, dipole moment is a vector quantity, and by conversion, it is depicted by a small arrow with the tail on a negative center on and head pointing towards the positive center. But in chemistry, presence of dipole moment is represented by the crossed arrow put on Lewis structure of the molecule. The cross is on positive end and positive end, and arrow head is on negative end. For example, the dipole moment of H of may be represented as this arrow symbolizes the direction of the shift of electron density in the molecule. Note that the direction of crossed arrow is opposite to the conventional direction of dipole moment vector. Now, in case of polyatomic molecules, the dipole moment not only depend upon the individual dipoles but also on the spatial arrangement of various bonds in the molecule. In such case, the dipole moment of a molecule is the vector sum of the dipole moments of various bonds. For example, in H2O molecule, which has a bent structure, the two OH bonds are oriented at an angle of 104.5 degree. Net dipole moment of 6.17 into 10 to the power minus 13 cm coulomb meter. Now 1d is equal to 3.33464 into 10 to the power minus 13 cm is the resultant of the dipole moment of two OH bonds. Now the net dipole moment mu is equal to 1.85d, 1.85 into 3.33564 into 10 to the power minus 13 cm is equal to 6.77 into 10 to the power minus 13 cm. The dipole moment in case of BF2 is 0, and this is because the two equal bond dipoles point in opposite directions and cancel the effect of each other. The intraatomic molecule, for example, in BF3, the dipole moment is 0, although the BF bonds are oriented at an angle of 120 degree one to one another. The three bond moments give the given net sum of 0 as the resultant of any two is equal and opposite to the third. Now let us study an interesting case of NH3 and NF3 molecule. Both the molecules have the pyramidal shape of with the lone pair of electrons on nitrogen atom. Although fluorine is more electronegative than nitrogen, the resultant dipole moment of NH3 of 4.9 into 10 to the power minus 30 cm is greater than that of the NF3.8 into 10 to the power minus 30 cm. This is because in case of NH3 the orbital dipole due to lone pair is in the same directions as the resultant dipole moment of the NH bonds, whereas the NF3 the orbital dipole is in the direction opposite to the resultant dipole moment of the three NF bonds. The orbital dipole, because the lone pair decreases the effect of the resultant NF bond moments, which results in the low dipole moment of NF3 as represented below. The dipole moments of some molecules are shown in table 4.5. Just as all the covalent bonds have some partial ionic character, the ionic bonds also have partial covalent character. The partial covalent character is of ionic bonds has discussed by Fajans in terms of the following rules. Dipole moment of selected molecule table 4.5. Electron pair repetition theory, VSEPR theory. As already explained, the Lewis concept is unable to explain the shapes of molecules. This theory provided a simple procedure to predict the shapes of covalent molecules. The main postulates of VSEPR, the shape of a molecule depends upon the number of valence shell electron pairs, bounded or non-bounded, around the central atom. Pairs of electrons in the valence shells repel one another since their electron clouds are negatively charged. These pairs of electrons bond tend to occupy such positions in space that minimize repulsion and thus maximize distance between them. The valence shell is taken as a sphere with the electron pairs localizing on the spherical surface at maximum distance from one another. The multiple bond is treated as if it is a single electron pair, and the two or three electron pairs of multiple bond are treated as a single super pair. Now, when two or more resonance structures can represent a molecule, the VSCPR model is applicable to any such structures. And the repulsive interaction of electron pairs decreases in the order lone pairs, then lone pair is greater than lone pair base pair, bond pair is greater than bond pair. Nahon and Gillespie in 1957 refined the VSCPR model by explaining the important difference between the ion lone pairs and bond for pairing electrons. While the ion lone pairs are localized on the central atom, the molecules in which the central atoms has no lone pair, and molecules in which the central atom has one or more lone pairs, as depicted in table 4.6. In the compounds of AB2, AB3, AB4, AB5, AB6, the arrangement of electron pairs and the B atoms around the central atom A are linear, trigonal plane, tetrahedral, trigonal, bipyramidal and octahedral. 4.6 Table geometry of molecules in which the central atom has no lone pair of electrons. Number of electron pairs, arrangement of electron pairs, molecular geometry and examples. 4.7 Table shape geometry of some simple molecules, ions with central ions having one or more lone pairs of electrons. Molecule type, number of bonding pairs, number of lone pairs, arrangement of electron pairs, shape and examples. And table 4.8 shapes of molecules containing bond pair and lone pair. Molecules type, number of bonding pairs, number of lone pairs, arrangement of electrons, shape and reasons for the shape acquired. Valence bond theory. Valence bond theory was introduced by Hattler and London 1927 and developed further by Pauling and others, and discussion of the valence bond theory is based on the knowledge of atomic orbitals, electron configurations of elements. Unit 2, the overlap criteria of atomic orbitals, the hybridization of atomic orbitals, and the principles of variation and superposition. A principle of very rigorous treatment of valence bond theory in terms of these aspects is beyond the scope of this book. Therefore, for the sake of convenience, valence bond theory has been discussed in terms of qualitative and non-mathematical treatments only. To start with, let us consider the formation of hydrogen molecule, which is the simplest of all molecules. Since the energy gets released when the bond is formed between two hydrogen atoms, the hydrogen molecule is more stable than that of isolated hydrogen atoms. Then the energy so called released is called bond enthalpy of figure 4.7. Forces of attraction and repulsion during the formation of H2 molecule. For figure 4.8, the potential energy curve for the formation of H2 molecule as a function of internuclear distance of the hydrogen atom. The minimum in the curve corresponds to the most stable state of H2. Orbital overlap concept, directional properties of bonds, overlapping of atomic orbitals, types of overlapping and nature of covalent bonds, sigma bond, pi bond, strength of sigma and pi bond, hybridization, important conditions for hybridization, types of hybridization, sp hybridization, sp2 hybridization, sp3 hybridization. Other examples of sp3, sp2 and sp hybridization: hybridization of elements involving d orbitals, formation of SF6 sp3 to d2 hybridization, molecular orbital theory, formation of molecular orbitals, linear combination of atomic orbitals, conditions for the combination of atomic orbitals. The combining atomic orbitals must have the same and nearly the same energy. The combining atomic orbitals must have the same and symmetry about the atomic molecular axis. The combining atomic orbitals must overlap to the maximum extent. Types of molecular orbitals, energy level diagram for molecular orbitals, electronic configuration and molecular behavior, bonding in some homonuclear diatomic molecules, hydrogen bonding, causes of formation of hydrogen bond, types of hydrogen bond, intermolecular hydrogen bond and intramolecular hydrogen bond, chemical bonding and molecular structure. Let's start करते हैं summary. Costell's first insight into the mechanism of formation of electropositive and electronegative ions related to process now to the attainment of noble gas configuration by the respective ions. Electrostatic attraction between ions is cause of for their stability. This gives the concept of electrovalency. The first description of covalent bonding was provided by Lewis in terms of the sharing of electron pairs between atoms and he related the process into the attainment of noble gas configuration by reacting atoms as a result of sharing of electrons. The Lewis dot structures symbols show the number of valence electrons of the atom of a given element, and Lewis dot structures show pictorial representations of the bonding in molecules. An ionic compound is pictured as a three-dimensional aggregation of positive and negative ions in an ordered arrangement called the crystal lattice. In a crystalline solid, there is a charge balance between the positive and negative ions. The crystal lattice is stabilized by the enthalpy of lattice formation, while a single covalent bond is formed by sharing of an electron pair between two atoms. Multiple bonds result from the sharing of two or three electron pairs. Some bonded atoms have additional pairs of electrons not involved in bonding. There are called lone pairs of electrons. The Lewis dot structure shows the arrangement of bonded pairs and lone pairs around each atom in a molecule. Important parameters associated with chemical bonds like bond length, bond angle, bond enthalpy, bond order, and bond polarity have significant effect on the properties of compounds. A number of molecules and polyatomic ions cannot be described accurately by a single law in structure, and the number of descriptions representations based on the same skeletal structure are written and this taken together represent the molecular ion. This is a very important and extremely useful concept called resonance. The contributing structures of canonical forms taken together constitute the resonance hybrid, which represents the molecular ion. The VSEPR model used for predicting the geometrical shapes of molecules is based on the assumption that electron pairs repel each other and therefore tend to remain as far apart as possible. According to this model, molecular geometry is determined by repulsions between lone pairs and uh, um, lone pairs and bonding pairs and bonding pairs and bonding pairs. The order of these repulsions belonging lone pair is greater than lone pair, bond pair is greater than bond pair. The valence bond approach to covalent bonding is basically concerned with the energetics of covalent bond formation, about which the Lewis and VSEPR models are silent. Basically, the valence bond theory discusses of bond formation in terms of overlap of orbitals. For example, the formation of hydrogen 2 molecule from two hydrogen atoms involves the overlap of 1s orbitals of the two hydrogen bonds, two hydrogen atoms which are singly occupied. It is seen that the potential energy internuclear distance, bond distance, and the energy touches a minimum. Any attempt to bring the nuclei still closer, resulting in a sudden increase in energy and consequent destabilization of the molecule because of orbital overlap. The electron density between the nuclei increases, which helps in bringing them closer. It is, however, seen that the actual bond enthalpy and bond length values are not bond obtained by overlap alone, and other variables have to be taken into account for explaining the characteristic shapes of polyatomic molecule. Pauling introduced the concept of hybridization of atomic orbitals, sp2, sp3 hybridizations of atomic orbitals of beryllium, boron, carbon, nitrogen, and oxygen are used to explain the formation and geometrical shapes of molecules like beryllium chloride, boron chloride, HCH4, NH3, and H2O. They also explain the formation of multiple bonds in the molecules like C2H2 and C2H4. Molecular orbital theory describes bonding in terms of the combination and arrangement of atomic orbitals to form molecular orbitals and that are associated with the molecule as a whole. The number of molecular orbitals are always equal to the number of atomic orbitals from which they are formed. Bonding molecular orbitals increases electron density. Molecular orbitals have the lower the region of zero electron density between the nuclei and have more energy than individual atomic orbitals. The electronic configuration of the molecules is written by filling electrons in the molecular orbitals in the order of increasing energy levels, as in the case of atoms. The Pauli exclusion principle, the Horn's rule are applicable for the filling of molecular orbitals. Molecules are said to be stable if the number of electrons in bonding molecular orbitals is greater than that of in antibonding the molecular orbitals. Hydrogen bond is formed when a hydrogen atom finds itself to be between two highly electronegative atoms such as fluorine, oxygen, nitrogen. It may be internuclear, existing between two or more molecules of the same or different substances, are intramolecular, present within the same molecule. Hydrogen bonds have a powerful effect on the structure and properties of many compounds. Chemical bonding and molecular structure. केमिकल बॉन्डिंग एंड मॉलिक्यूलर स्ट्रक्चर हम देख रहे हैं 11th क्लास केमिस्ट्री एनसीईआरटी, जिसमें हमने वन शॉट सीरीज स्टार्ट की है। अब केमिकल बॉन्डिंग एंड मॉलिक्यूलर स्ट्रक्चर का हमने वन शॉट सीरीज में कंप्लीट किया है, जिसमें हमने पहले से देखा, जिसमें हमने स्टार्टिंग से देखा यूनिट 4 में केमिकल बॉन्डिंग एंड मॉलिक्यूलर स्ट्रक्चर में कोसेल्स लॉ, लेविस अप्रोच फॉर केमिकल बॉन्डिंग, ऑक्टेट रूल, कोवेलेंट बॉन्ड, Lewis representation of simple molecules, the Lewis structure, the Lewis representation of some molecules, formal charge, limitations on the octet rule, ionic and electrovalent bond, lattice enthalpy, bond parameters, bond length, bond angle, bond enthalpy, bond order, resonance structures, polarity of bonds, the valence shell electron pair repulsion theory, VLCPR. देन कुछ स्ट्रक्चर्स देखे हमने 4.6 टेबल, 4.7 टेबल, 4.8 टेबल, देन वैलेंस बॉन्ड थ्योरी, then orbital overlap concept, then directional properties of bonds, then overlapping of atomic orbitals, then types of overlapping of nature of covalent bonds, then strength of sigma and pi bonds, then hybridization, then types of hybridization, then other examples of sp3, sp2 and sp hybridization, then hybridization of elements involving d orbitals, then a molecular orbital theory, then formation of molecular orbitals, linear combination of atomic orbitals, then conditions for the combination of atomic orbitals, then types of molecular orbitals, then energy level diagram and of for molecular orbitals, then electronic configuration and molecular behavior, bonding in some homolinear and diatomic molecules, hybrid hydrogen bonding, cause of formation of hydrogen bond, types of hydrogen bond, intermolecular hydrogen bond and intramolecular hydrogen bond. then हमने समरी देखी. प्लीज़ लाइक शेयर एंड सब्सक्राइब. थैंक यू सो मच फॉर वॉचिंग. हमने 11th क्लास की केमिस्ट्री स्टार्ट की, जिसमें हमने वन शॉट सीरीज स्टार्ट की एनसीईआरटी की, जिसमें हमने ये सब देखा, कुछ स्ट्रक्चर्स देखे, देन बॉन्ड ऑर्डर देखी, बॉन्ड एंथैल्पी देखी, देन लेविस रूल देखा, ऑक्टेट रूल देखा, देन कोवेलेंट बॉन्ड देखा. केमिकल बॉन्डिंग एंड मॉलिक्यूलर स्ट्रक्चर यहाँ पर खत्म होता है. प्लीज़ लाइक शेयर एंड सब्सक्राइब. थैंक यू सो मच फॉर वॉचिंग.